I'd like to go into a little bit more detail on exponential and logistic growth models, and also talk about the calculations involving population change and population growth rate. So the carrying capacity of an environment is the maximum number of individuals in a particular population that an environment can support. Now, the carrying capacity and whether or not that population is close to carrying capacity is going to affect how quickly that population is growing. And we calculate the population growth rate by multiplying the change in individuals, birth minus death, times the number of individuals in the population. That's our basic growth rate. But we can calculate the effect of that carrying capacity on the population as well. And we do that by adding a new term into our calculations, this carrying capacity term, where we calculate carrying capacity, the number of individuals the environment can support, subtract the number of individuals already present in the environment, and then divide by the carrying capacity. Now, as the population reaches or gets close to carrying capacity, the population growth rate is going to slow down, and that's our logistic growth rate. Population numbers are small as they begin to increase. Population begins to increase very, very quickly. If it were to continue, we would see exponential growth rate. But we all know that the population cannot be sustained indefinitely in ever-increasing numbers. And so as that population gets closer to the carrying capacity, the growth rate is actually going to slow down as resources begin to run out. Now, in general terms, we can think about how this effect of carrying capacity is going to impact our growth rate. When we calculate this new term, if that new term is small, you can think of it as multiplying by zero or multiplying by something very close to zero. And when you do that, you get very little or no change in that number that you're multiplying by. If you multiply by zero, the answer is zero, which means there's going to be no growth, no change in the population. And if that number is small, very close to zero, there's going to be very little change in the growth rate, which means that that population is entering this logistic growth phase where it begins to slow down. So when your population is close to carrying capacity, the effect of carrying capacity on the growth rate is that it's going to limit it and slow the growth rate down. When that new term is large, that means that the population is not close to their carrying capacity yet. Now, if you just think about what's going on, if the population is nowhere near carrying capacity, they're still in their exponential growth rate. So if that new term is large, meaning that it's close to 1, it's not going to affect your rate very much, your original rate, your R times N. And you can think of this as if you multiply something by 1, it doesn't change. Your growth rate isn't changing, which means that that growth rate is still in the exponential, the growth rate is still occurring at an exponential rate. That means that the population is far from carrying capacity. If you recall from lecture, the point halfway between 0 and the carrying capacity is where we have maximum growth in our population. And so when our population is not large compared to the carrying capacity, there's room for that exponential growth rate to happen before carrying capacity begins to affect population level. So let's look at two real populations and apply this to a real situation. Now, the first thing we need to do if we're going to calculate the effect of carrying capacity on growth rate is to actually consider the growth rate, calculate what the growth rate is. So we do that by multiplying R times N. And in order to determine R, we need to know the birth rate and the death rate for the animals that we're talking about. And then, of course, this is a change over time. So for this population, we're going to look at a 10-year period. So 1960 to 1970. The moose population is shown in purple here. We can see the population actually extends for about 40 years between 1955 and 1995. The wolf population is shown in red. Now you can see the reaction of one population to another. When the wolf population is low, the moose population can increase. There's a bit of a lag period, but once the moose population gets high, those wolves can increase because now their prey are abundant. As the wolves get high, the moose begin to drop. Now, this is a common situation that we see in real world population ecology. When a food source is high, the population of organisms responds, and when the food source is low, the population responds as well. And so there's sort of this give or take between predator-prey relationships. So let's start with the moose population, and let's say that in 1960 the moose population is approximately 60. Now this is just an estimate. We've got our number of moose on the right-hand side, number of wolves on the left-hand side, so this is kind of a double graph. And I've made up numbers, so these numbers are kind of estimates based on our graph, but the trends are going to be the same. So let's say the population starts at 60 in 1960, and over the next 10 years, there are 2,000 individuals that are born in the population. Now, that doesn't mean that these 60 individuals birth 2,000 moose. It means that over 10 years, these 60 and all their descendants birth 2,000 moose. Now, let's say in that time frame, only 500 die. So the first thing we need to do is calculate R for our population. From there, we can calculate our growth rate. So to calculate R, we're going to take the birth rate minus the death rate. So 2,000 births minus 500 deaths divided by 60 individuals in the starting population. Now our R value for this is going to be 25, and that's okay that it's greater than 1. It means that our population is growing exponentially. It means that the population is growing very, very quickly. To determine the overall growth rate, to actually calculate the number of individuals that the population has increased by, we're going to multiply that by the number of individuals in our population. So new population growth, the number of individuals that have been added to the population, is going to be 25 times 60, or 1,500 more moose in 10 years. So our new population size, taking into account births and deaths over 10 years, is going to be 1,560. Now let's consider the effects of carrying capacity on this population. To do that, we need to multiply our R times N, our growth rate for the population, by the effect of carrying capacity. Now let's say that the environment can support 10,000 moose. So let's see what the new growth rate is when we consider the effect of that carrying capacity. So our new term is going to be the carrying capacity, 10,000, minus 60, the number of individuals in our population, divided by the carrying capacity. When we calculate that, we get 0.994. So this term is close to 1. And if you remember from the first slide that I showed you, that means that the population growth rate won't change much, because it's like we're multiplying this R times N value by 1. If you multiply it by 1, it stays the same. We're multiplying by something close to 1, which means this growth rate is not going to change much from what we expected. And that means that carrying capacity is having very little effect on the population yet. And that makes sense, because if we can support 10,000 individuals and there's only 60, there's a lot of room for this population to grow. So if we take into effect carrying capacity, multiply that by our old population growth rate, we can see that we get a new population growth of 1,491. That means our new population size is 1,551. It's very, very close to our current population growth rate. So that means that carrying capacity is having very little effect. The population is growing very quickly. In fact, the population is growing exponentially. Let's look at the wolf population now and see what's happening over there. So for the wolf population started at 20 individuals in 1960. In the 10-year range that we're interested in, there were 50 births and 40 deaths. So just thinking about this population, you might realize that this population is not going to grow quite as fast as the moose population. So let's start by calculating our change in the population by determining our growth rate. So 50 births minus 40 deaths divided by 20 individuals in the original population. So for the wolf population, R is going to be 0.5. Now you can see by just comparing 0.5 and the moose growth rate that the moose population is growing much more quickly. The wolf population is growing much more slowly. It's still growing, but it's growing more slowly. So to determine the change in the population size, we're going to multiply that times n. 0.25 times 20 individuals in the population means that we're adding 10 new individuals to the wolf population in that 20-year period. So our new population size is going to be 30. Now, let's look at the effect of carrying capacity on the growth rate. Let's say that the carrying capacity for the wolf population is 45. Now we already have 20 individuals. The difference between 20 and 45 is not nearly as great as the difference in carrying capacity and population size for the moose population. So we could already expect that our growth rate is going to be smaller for the wolf population. So let's calculate our new term. The new term, carrying capacity minus population size, 45 minus 20, divided by carrying capacity, comes out to 0.56. Now this is right smack in the middle between 0 and 1. Remember, if this new term is 0, the carrying capacity is having a large effect on the population size. If it's 1, carrying capacity is having little effect on the population. This rate is right in between. So that means we should expect there to be some growth, but the growth isn't going to be as great as we would expect for an exponentially growing population. And when we take that carrying capacity term into consideration, we find that R times N times 0.5, sorry, this should be 0.56 here, is going to equal to a change in the population of 5.6 individuals. Now we had calculated that the new population was going to add 10 individuals. We only added 5.6. This means that carrying capacity is having a little bit of an effect on this population. The other thing that might be happening is that we're still at the bottom of the logistic growth curve, which means the population is too small to be experiencing exponential growth, or there could be some other factor that is affecting this. Maybe there are more individuals dying than expected. But in either case, this population is not growing nearly as quickly. It's still growing. Our new population size, when we take into effect carrying capacity, we get 26.6 individuals. So this is saying that whatever's happening to the population, the environment is limiting the effects, or I'm sorry, limiting the number of individuals that can survive. So just sort of a quick summary. Let's put some growth curves on this population. So our moose population is experiencing exponential growth, and you can see that in the curve here where that growth rate is shooting up. The wolf population is growing more moderately. It's maybe not quite at this little bit of an exponential curve here, or if we look at it over the entire period, if you sort of took an average, you can see that that slope is not going to be as great as the moose, and the wolf is experiencing some ups and downs as well. Now this sort of makes sense because if the moose population takes some time to grow, the wolf population is also going to lag behind a little bit. Now both of these populations, even if they are a perfect textbook case, are still going to oscillate around that carrying capacity. Because when things are good, they're going to overshoot, they're going to produce more individuals than can survive. And then they're going to kind of crash a little bit. And then things are going to slowly start to settle down. And there's going to be less overshooting in the population. If these populations are stable, we'll see them both at their carrying capacity and eventually they'll settle down.